Good afternoon, good evening, good morning to people from all over the place. It's my great pleasure to be here in Sweden with the two speakers who are going to speak today, Gunnar Holmberg and Nicolette Lakeman. Gunnar received his PhD in machine design from Linköping University, Linköping, Sweden in 2003. Currently a director of business development at Saab Aeronautics, Linköping, Sweden, and an adjunct professor with the Collaborative Product Development Department of Management and Engineering at Linköping University. He has previously performed research on product development for complex systems with long life cycles, and he has held various management positions at Saab over the years, including forming and leading international R&D collaborations. His research interests include management challenges related to the emergence of complex intelligent products and systems. Dr. Holmberg is a member of the Royal Swedish Academy of Engineering Sciences and member of the Executive Committee for ICAS, the International Council for Aeronautical Sciences. Then we have Professor Nicolette Lakeman. She received a PhD also from Industrial Management from Linköping University in 2001. She is currently a professor of industrial management with Department of Management Engineering and Engineering at Linköping. She has previously performed research on innovation in complex and organizational settings, including buyer-supplier collaboration and customers' role in the knowledge supply chain of innovation, interim collaboration on digitalization projects, knowledge integration in open innovation. Our current research focuses on management challenges related to the emergence of complex intelligent products and systems following the introduction of artificial intelligence solutions. This includes questions related to how safety, criticality, and systems generativity can be combined, how decisions can be made concerning complex intelligent systems, how organizations can be designed, how they can work with others in ecosystems, and how they can harness complexity. Dr. Lakeman has previously served in the roles of Director of Studies, Division Head, and Deputy Dean with responsibility for research at Linköping University. They are really people with enormous amount of experience, and you will see that in their presentation, and I hope you enjoy it and get a lot of insights into the way complex systems, digitalization, and artificial intelligence play a role in the way society is going to be evolving over time and has evolved over time. Thank you, Gunnar. Thank you, Nicolette.
It's all yours.
Thank you.
Thank you, Sab, for that kind introduction, and it's a great pleasure to get the opportunity to do this presentation, and we hopefully can contribute to this very nice series of lectures that you have arranged. I and Nicolette, we have been working together since 2015, basically, and working tightly together. So everything we are presenting together is the fruit of close collaboration, and we usually say that we would not be able to do any of this without doing it together, actually. So it's really a work of us together. Having said that, I may do most of the presentation today, and Nicolette is filling in, and we look forward to questions and being challenged, and we will try to respond together to that. Very nice introduction on what we are dealing with, but already when we started 2015, we began to look at complex systems together and what was happening in complex systems, and we were in particular looking at recombination possibilities and things like that in the beginning. And fairly soon we experienced that there are a number of things that are happening in parallel that could have potentially quite a strong impact on society. And one of those things is a lot talked about today, and that's AI and the use of machine learning and other technologies that may contribute to society. And of course, we talk more about that. At the same time, we could see that there was a lot of movements on how can we contribute to society in a better way. And one of the things that probably was missing was considering the context of our complex systems and being able to reflect the dynamics of that and the consequences of the context based on how we're dealing with the systems. And one way to see it is that we have developed a lot of infrastructures and systems that have improved our society, but we have done that with quite static boundaries to the systems. And maybe that's one of the reasons why we are facing so many challenges relating to, for example, sustainability and so on. So there is a lot of things coming to that. And from this, we have shaped a group and a project that is focusing on what's happening when we get AI into the society and how can we do that so we benefit from it and we minimize the negative consequences, basically. So we can ask a couple of questions in that. Can we do what we do in a better way? Can we be more sustainable? Can we be more efficient? Can we be more equitable and so on? So that's kind of reflecting the purposefulness of what we're doing. But we can also ask questions, can we do things we can't do today? So it's both the question of scaling, being better at doing it, but also finding things that we cannot do. And one way of illustrating this is the picture we got from NASA here, and that is illustrating the world as a connected system. And it requires a lot of thought and strategies in order to set the boundaries of the systems we're doing as they are interconnected as part of the world. So rather than starting with isolated system, it's looking at what happens with the systems and infrastructures in a context that is our focus. And then we can say a little on the group.
Yeah,
perhaps.
we can say at the time when we started 2016, 2017, and when we wrote a manifesto on this, we were quite unique. Many people started talking about AI, but not many took into account this context of complex systems or even the societal context. So what we defined for the overall program actually that we're running, and I'm just going to introduce this very quickly, and then we were just presenting part of it for today's lecture, but we could talk much more about it. But our overall goal is to understand how organizations can be managed responsibly in a purposeful way, to address actually the emergence of artificial intelligence in this complex context of complex, what we call intelligent systems. And as you understand, this requires not only one perspective, many perspectives. It's engineering, it's management, it's technology, considering social aspects and reflecting also, not the least, this wider demand for purposeful management. And this purposeful management is referring to that there increasingly we need to understand that there needs to be a higher purpose of an organization beyond what we from traditionally have considered as some kind of economic exchange or economic benefits or profits, but also reflecting something that is more aspirational, that is reflecting all the things that we're talking about today and that are so important to address our societal challenges, for example, sustainability, but also privacy, safety and security also increasingly. So this is very much what we see tied to basically all the sustainability goals that are there. We managed during the past 5-6 years to start a research group. We have 4 PhD students and 2 postdocs doing research, and we ourselves are also quite active in research. And our PhD students and postdocs, and we do research in different kind of areas on a little bit different aspects of the topic. We have, for example, one PhD student looking into kind of this issue when AI becomes part of systems that are, have a high degree of, for example, safety criticality. And when AI then brings some kind of generativity with it, how can these two be combined, and what you need to think about that? And she is studying in a context where it is looked into future search and rescue in public safety domain. We have another PhD student who is looking more at decision making and having healthcare as her study domain with personalized medicine and not least breast cancer as some of her cases. So how can AI solutions assist radiologists in making decisions and diagnosis, and how does this affect healthcare organizations and systems? We have another PhD student looking into when complexity is increasing such that basically it becomes beyond human cognition, and she's studying this in the context of smart city. And we have fourth PhD student looking into different development or design logics, where traditionally in complex system there is some kind of model-based logic, which is now complemented increasingly with data-driven, and he's mostly looking into automotive and aviation. And in the middle, you see also some of the topics that we're interested in, and I can assure you this is a long, long list. This is not the complete list. PhD students, they look into industrial ecosystems, for example. So we try to create some momentum to study this topic, but basically there are so many different aspects that need attention and that are interesting.
And we're still a small group.
We're still quite a small group, yes. And we see that this is so important, not only kind of that individual organizations we need to understand better how they should meet the future with artificial intelligence and how they contribute to the development of complex systems. But we see that what is happening is that basically all our critical infrastructure in society is affected by this. So many complex systems are representing or are part of critical infrastructure in the energy sector, healthcare, transportation, financial, ICT, water, food, and so on. And this is just the division of the European Union. I think there are some different kind of lists, but I think you recognize it. And we're going to dive a little bit deeper into one of them with an example, I think, which we would like to discuss, and that's the transportation sector.
Let's see if this works. We are then looking at self-driving cars, and hopefully you can see the film on the screen as well, that is offering a vision for the future rush hour. And not sure it's working like traffic in India, but maybe a mutual adjustment is well reflected in this. Anyhow.
This is, of course, fabricated, but it basically reflects this complex issue of self-driving cars, autonomous systems, which is not only the car in itself, but there's so many more aspects, because there's so many different participants in transportation, but also different transportation and the infrastructure behind it. So all of these kind of need to be addressed in some way.
And we can see that in the last 10 or 20 years, there have been a lot of efforts to assist the driver in driving the car, and there are perhaps some efforts on the transport system as well, but there's much less attention to that. And we have worked with an example of this based on works by Bonnefon, a psychologist in Toulouse, and he's building on works from Oxford by my societal sociological psychologist.
I think she was a psychologist from the beginning as well, but
anyhow, you're probably familiar with the problem here, but we're taking it one step further, I hope, than you have seen before, and that with the purpose to highlight what we need to do in order to connect society with a technical solution. And The experiment that Bonnefon did contained 10 different scenarios, and they were done with a car that was driven by yourself or by an autonomous car. And I
Happy
think
birthday.
we'll just take one example. There is someone that should mute, I believe. And anyhow, so this example is coming from a trolley example that you've seen probably. And we have the situation where a car is coming and driving and you are the one driving this. And to your surprise, there are 10 pedestrians appearing in front of you. And the extreme case of this situation is that you have only two options now. One is to swerve off the road and hit the wall. And that will mean that you are getting killed, but the 10 pedestrians are surviving. The other one is that you stay on the road, save your own life, but it will kill the 10 pedestrians and you will be unharmed. So that's along the lines, and questions then come, what would you like an autonomous car to do, and so on. And when we look at the findings from Bonnefon's study of this, in 2016, he says that it's probably a need for regulation for autonomous vehicles in order to solve this, but it's also that such a regulation might be counterproductive. And looking into that, people tend to agree that everyone would be better off if an autonomous vehicle is utilitarian, minimizing the number of casualties or injuries in traffic. But everyone also have the personal incentive to drive vehicles that protect themselves at all costs. And if both types of vehicles were allowed on the market, few would be willing to ride utilitarian autonomous vehicles. So a regulation might solve this, but may as well delay implementation of life-saving technology. And Bonnefon's conclusion of this was that moral algorithm for autonomous vehicles will need to tackle more intricate decisions. We hope that psychological studies inspired by our own will inform this discussion. So that was his starting point. We used this in a course on corporate social responsibility, and we asked the student to comment on this as well. And we then got a number of interesting answers, and we have put bold text on the ones we want you to pay attention to now. And the first then is bullet number 3, and that position of the student was, I would not buy a car that kills me if someone throws himself in front of the car to commit suicide. Another one was referring to his or her country. In my country, people jump in front of cars to rob them. I would definitely not kill myself for that. So that's kind of showing the complexity of the situations that we have to deal with, and it's really difficult to handle that. Then people commented on, should it be randomized in kind of lottery who's surviving, or should it be something that is determined? And in the group there were representatives of both perspectives. A random choice would be the most appropriate, and another one thought that random is not an option. I want to know how the car is programmed. So that is in a sense showing the difficulty to meet everyone's views on this, and also how to debate it in society. And then looking at the way forward, there were comments like the traffic environment needs to be adapted to autonomous vehicles, and there are also perspectives that are not expecting any contributions from technology, like I'm not interested in autonomous vehicles. Technology like this ruins the world. So that's also kind of spectrum.
Maybe this was most interesting because it was for an engineering students.
Yeah,
so
slightly unexpected.
Yeah.
So then we can ask, what is it that Bonnefon is suggesting that we should debate and discuss and agree? And we can look again at this trolley problem, and what is then the societal challenge or problem that needs to be addressed? Well, that's to debate who is going to survive and who is going to be sacrificed, and that can be quite dependent on values in different societies, and there are an extreme or almost infinite amount of possible alternatives where possible alternatives. It's really challenging for a society to be able to master and conclude on a discussion like that. And the engineering problem that we are dealing with, that is well, hardly possible to identify. And if we are able to define that problem, how could it be solved? So that's really complex and difficult to deal with. And then we can ask ourselves, are there other ways to view this problem? And as we said, that we have backgrounds on studies in aviation, for example, it's not so far-fetched to look at a safety approach where we, similar to aviation, are analyzing the safety and we are distributing the safety of the system, and we work from a level in aviation, it's 10 to the -9, meaning that catastrophic accidents with more than one person being killed should happen less than 1 over billions flight hour, and similar for different levels then. So then we can start a debate in society. How safe is safe for a traffic system? And a starting point could be that we talk about something that is equally safe as when we have human drivers of the cars. But that is not good enough probably, because there will be change in who is getting injured and who is getting killed as a consequence of a different driver behavior of an autonomous car. So we probably need to be safer, but how much safer? Should we ask for 10 times? That's a huge leap forward, but it's also perhaps feasible to design a system that is meeting that. Or should we demand 100 times? And then we can see perhaps that such a system would be extremely expensive and extremely controlled, so that will not be possible to implement probably. Numbers are just assumed here. But the consequence of saying 100 instead of 10 then would be that the system will not be implemented and we will not gain a factor of 10 in traffic safety. So it's an important discussion, but still much easier discussion to have in society. And if we look at the engineering problem, yeah, you want to fill in?
No, yeah, I just wanted to kind of repeat the main message here that, and I think we see that also in the discussion related to artificial intelligence in society. There's so many different aspects that in the end it becomes an impossible discussion to kind of make sure that AI is safe, that it's transparent, that we can trust it, etc. And perhaps we need to consider the perspective that we take to understand this, so that we actually can address something for real, rather than staying in a discussion that cannot be solved.
Exactly, and what we see here, I think, is that if we discuss level of safety, we have methods for designing a safe system, and that makes the engineering problem useful as well.
Yeah.
And that underlines the importance, as you say, that it's so important to find the right way to pose a question. And then if you look at what Bonnefon was coming back 3 years later in 2019, saying that the problem is that we currently have no idea where to set the cursor. It's straightforward that we want autonomous cars to lead to fewer fatalities, but we do not know how these fatalities ought to be distributed among the road users. And in a sense, he's admitting that it's not the possible way to ask the question, but we need to do it in another way. So,
and if you think of the years that these studies were published, and he has done work after that as well. In 2016, I think the hype with autonomous car was on its high point, perhaps, and everybody was expecting that this would become reality. At least perhaps in the European or American context. I don't know how it is in India, where the traffic system is working perhaps a little bit more, well, you know, sometimes things chaotic, and maybe we can call it mutual adjustment. But what we have seen now is that we have had this period where we kind of have understood that, well, it is not a reality completely. We see a lot of driver assistant technology have become a reality, but not a complete autonomous car, and perhaps we don't see that happening really in a very near future even either. So the discussion is really important, and considering how to address the problem in the best possible way is something that we need to think about more.
So then to the second topic, as was mentioned by Sabine in the beginning. Now we talked about the connection from society to engineering management, basically. And the second thing is the case of avionics, where we have been studying avionics for many years now, and looked at how has that been evolving, and we have then done a process study on this with a focus on Saab aircraft and the history of Saab, and we have focused on properties like safety, security, and reliability. And the reason for paying attention to avionics is that this business was one of the pioneering adopters of computing, of sophisticated control systems, of sensing technologies, integrated with physical systems and health monitoring and so on. So there is a lot of brave steps taken in this business.
But we can say also at the time there was so much talk about digital innovation and the digital transformation, and that was something that was happening suddenly. So we felt we need to kind of put attention to a case where we have seen this going on for a long time, basically, because basically this digitalization and increased digital functionality, and not only in avionics or in aircraft, but also in some other has been going on for a long time. So we need to try to understand and capture the learnings from that.
And an additionally interesting thing is that we could see that there was an accelerating introduction of new functionalities into aircraft and into the air traffic system. So it was kind of growing in intensity. And we like the three pictures here that we illustrate with as well, where the first picture to the left is the Wright brothers when they in 1903 made the first flight, and you don't see much of a cockpit or instrumentation in that aircraft, but it's being handled solely by the pilot and by the observation, and the aircraft was unstable, so it was really difficult to fly this aircraft, and completely compensated by the pilot. Quite impressive, we have to say. Then if we go to the late 1940s and 1950s, we have the example of the C-47 or the DC-3 aircraft, which is one of the most manufactured aircrafts in the world. There you can see that the information provided to the pilots is composed of many different types of information given piece by piece, and the pilots are to a large extent trained to how to compile this information in order to understand the flight state and how to operate the aircraft, and being able to detect faults and deal with faults and so on. So it was quite a challenging time to fly, and it was really demanding to learn to do this in a safe way. And then that was, of course, reflected in less safe operations as well. And to the right, we have a Boeing 787, a product of 2010, basically. And that is an aircraft that has computer screens, and information is compiled, and a full flight state is shown. It's also status of the system, and in case there is something that is not working according to plan, there are checklists to work through to actually compensate for the errors. So there is a guidance for the pilot how to resolve issues and so on. So much easier to fly an aircraft like that, and the avionics has taken over much of the pilot's role in this, and that is also reflected in the degrees or levels of safety that you have in an aircraft. If we start to take a look at the architectures of these aircraft, and I mean we dig back to material from the 1950s and 60s, and we were quite fascinated by the individuals that we could read were driving this in Sweden, in this case, when we look at Saab, and we had Börje Langefors, for example. That was, if we talk about open innovation today, we can see how he was traveling the world scouting for technologies and solutions.
First computers, and came back
Yeah.
to Sweden. And I think maybe we can say something about the visionary from the beginning, where already very early we could see documented that there were some very important underlying principles that have been following the evolution of avionics at Saab until today, you can say, where one of the principles was to separate safety critical from non-safety critical functionality.
And the other important principle was to gather all the information so that can be available for the complete system. So if we look at this in the architectures, we're sorry that the quality of this picture to the left is poor, but it's actually a picture from early 60s, so I think we can excuse it. But this is then not a complete system doing everything on the aircraft, but it's something that is offering targeting support for the aircraft. So it's just a single functionality basically in the aircraft, and it's listing some external references, but already there we can see some communications. But this was then used for the Viggen aircraft that was developed during the 60s, and the principles that Nicolette mentioned are quite visible in this architecture. If you look in the middle of this architecture, you see the CK-37. The number of the aircraft was Saab aircraft number 37, and CK stands for central calculator in Swedish, centralkalkylator. So it's kind of a integrating computer, and you can see many different functionalities being listed in this architecture, and this is then drawn in the mid-60s, this picture. And I think if you look at this and you're in aviation, you would recognize many of these functionalities still today. So the two principles of gathering all data, making that available, dividing safety critical and non-safety critical, and then the functional structure of this is something that you can trace back to the mid-60s at least, and maybe even before that. But I think that's fascinating actually, how they were able to both do this and formulate so general principles.
But this was the first aircraft with a computer on board at Saab.
Yeah. And similar things were of course done in other nations as well. And the material we have on the principles was published at an AIAA conference in the US in 1969, and really fascinating to read their expectations on computers. So going from this, we go to the 80s and the development of the Gripen aircraft that has been developed in 3 generations and is having a continuous development as well. Here we can see that the first version of the Gripen is maintaining the same type of structure, but it's moving away from the central computer for sharing information, and data buses are playing a more central role in this. And it's an unstable aircraft, so the flight control system is fully electric and a key component, and that means that we have critical, and maybe the most critical system in the aircraft is being realized by software now. And that is complemented with a system computer, and that is dealing with the mission-oriented task and supporting how to keep the systems that are operating the aircraft integrated.
At this point in time, we can also say that complexity was to such a level that it was difficult for one person or a small group of persons to kind of oversee and understand all parts of the system, which also made that more formalized methods, like some simulation was started to play a role and modeling. And before, I think what could be seen in the organization that there were a few key individuals that had a very large knowledge of the complete system, basically, and they were seen as these, visionaries, or what you can say, architects, really deep architectural leaders. Yeah,
maybe 10 people together understanding the complete system. So it's a sufficiently small group, but now it's expanded beyond that. So here we needed more formalized methods in doing that. And what we've seen in the study is that both the flight control system and the use of glass cockpits offers a lot of flexibility to the design, but it's also much more challenging to create this. Maybe the architectural scheme doesn't reflect the growing complexity, but if you go into details, there are layers in this that show something that is much more interconnected and much more critical in terms of its behavior. Following this, there was a new generation of Gripen during the 90s, and data buses are playing a more central role, and the dealing with different onboard vehicle systems like the fuel system, like the air conditioning and so on, was put together to be much more integrated, and by that enabling better health monitoring and dealing with all those nitty-gritty things of flying an aircraft in a much better way, offloading the pilots during operation and supporting the support personnel when doing the ground handling. And it goes along the same line that complexity is growing, new possibilities are being achieved, but it's also that the complexity here is getting to a level where we can see it's being difficult to update at the same time as there is a need to actually update more frequently. And that is the final step of the ones we studied, and the current version of the Gripen, the E version, where we can see that a lot is based on platform-oriented architecture, layered architecture, where we have partitions, and partitions are being developed based on safety criticality, and visualization systems are being developed in a way where criticality is reflecting, such that you have a screen, you can prioritize safety critical information, and that can never be disturbed by less critical information, and that is offering you possibilities to work more rapidly with the non-critical information on the screen as well, but not endangering the critical information and so on. So there is a huge work on making this happen, but it's opening up almost a new world of possibilities for how to evolve the aircraft over time.
Yeah, it's a system challenge, it's an organization challenge, and it's something where even more sophisticated formal methods are playing a large role in the development.
Tools as well.
Yeah.
So if we summarize this, in a sense, we can talk about initial experiments in the 1950s. Pioneers were trying to understand what can we use this technology for, what are the problems we should solve with this, and that was on the Draken aircraft. Maybe we should have given you pictures before, but this is quite a unique configuration for the aircraft, the double delta it's called. Then we had in the Viggen a canard configuration, we had add-on functionality, and add-on means that it's not safety critical. If you take it away, the aircraft can still fly, but it's losing the benefits of this add-on functionality that in itself might be quite sophisticated, but not critically integrated. Then during the 80s and 90s, we had more integrated and safety critical functionality with the Gripen aircraft's flight control system and navigation possibilities connected to that. And the CD we looked at and the E version now that is actually combining add-on and critical functionalities, enabling more generativity and opening up a path for future functionality that is much easier to integrate. And I think this is what we studied here, but it's also something that paints the picture of how digitalization in advanced system has happened over 20 years. And even though we studied Saab primarily, we were also checking, of course, with other industry. And weren't we quite fascinated with the Concorde?
Yeah, we are very fascinated by the Concorde. It's kind of amazing to see what could be achieved at that point in time. And also we have studied a little bit the developments and innovations that kind of preceded the Concorde. But there's so many different aspects on this Concorde case as well. But we save that for another lecture, perhaps.
Yeah. But we can say that if you go to Paris anytime, take the opportunity to visit the Air and Space Museum in Le Bourget, where you can get much of the Concorde story. So we have papers on this. We are not concentrating so much on the detailed contributions in this lecture, but more painting an overall picture. And one paper is the digital transformation in complex systems. That's painting the full story, offering conclusions and ways forward. We have one that is then looking at the quest for combining generativity and criticality in digital physical complex systems. So could you say something about that, Brad?
Yeah, well, this is basically focusing on the latest development of the Gripen E and basically this layered modular distributed architecture, which is something that's not happening only at Saab, but it's something it is branch for the whole industry, basically, where we could partly characterize this more platform based thinking, where we saw that open source software was playing a role, but basically on a more standardization level, and that was then made more proprietary within the system, where we also saw that new opportunities were created for adding non-safety critical functionality to the system through some kind of containerization, we can say. So there are many different aspects in that, but more focused on the latest development.
So based on this, we basically continued with what happens with AI. And one paper we have that is then working more on the public safety context and the demonstration arena for that, is then looking at the AI in the context of complex intelligent systems and what are the engineering management consequences for this. And we will talk a little about that as a conclusion of the talk. So if we take the same structure as we did for digitalization, we have initial experiments, meaning that we look for standalone applications of AI solving isolated tasks or experimenting for future application. We have next step add-on functionality, again standalone functionality that does not endanger the system but contributes with functionality that makes the system better and more relevant. Then we have critical systems where we rely on AI to solve a problem that has severe consequences if it fails. And then finally, we have the level where we are combining this into something that is integrated and mixing AI, different types of AI and model-based methods and so on, So that's the step.
And basically, what we see that's similar to digital and the digital transformation, where we saw and through the avionics case show that it's more of an evolution rather than a revolution that takes place in one point in time. We expect and we see that also what is happening related to artificial intelligence will be, especially in the context of complex systems, more be of an evolution, which will take longer time than we expect today, even though things are going fast. New things are happening all the time.
And we have tried to reflect that, and we have tested it on many. Then how can we map and understand our current situation? And this is perhaps 1 year old now with the latest updates, but basically we can see that AI is attracting a lot of interest, and a lot of people are experimenting, trying to understand what AI means to what they are doing and how they can benefit from it. Large language models and general purpose technologies like generative AI are experimented with. And then if we go to add-on functionality, we don't see so much of this that's being experimented, but we can see applications in financial, in medical screening, in digital marketplaces, social media, and natural language processing. But this is really the level where we can see early applications of AI is showing up, and not endangering things, but when it comes to...
Basically, that is where we are today. Everybody's trying to make sense on a personal level. What does ChatGPT mean for me? How can I use it in some applications in industry and also in public organizations? How can we benefit from AI? And studies are done. That is basically where we are in this making sense exploration phase very much.
And we really struggle to find applications that are critical today. And if we are generous in our understanding on this, we can see that driver's assist systems in cars, for example, and other isolated functionalities contribute to the safety, but it's not really that they are safety critical in the sense that then the car is crashing or something if the system fails. So that's really when it's taken to the next level. And as we said, we expect AI to contribute in a more complex context. So it's really at this level where we can expect the important influence on society.
Benefits.
This is also the level where it's becoming interesting from the management point of view that we are looking at, and the design point of view, because on the first two levels you can see that those are more or less self-organizing individual efforts or standalone efforts, but here we need to fit into a complexer situation and solving that. So that is really the interesting upcoming problems, challenges. And then we have some takeaways.
Yeah, the takeaways are perhaps rather simply formulated, but more difficult to put action on, but nevertheless very important. I think it cannot be emphasized enough, and we show that also through our studies, that basically the societal benefits from AI, they will materialize in complex contexts. So we can talk about all different apps and applications, and they can of course make a difference as well. But if we really want to achieve societal benefits on a larger scale, then we need to take this complex context into consideration and understand also many of the characteristics of this context, because it's not only the artificial intelligent technologies that need to operate in isolation. They need to work together and in combination and as part of a larger system with other technologies as well, and other aspects that need to be taken into account. And basically what we introduced in the beginning, where we talked about that many of the issues on our Earth are interrelated or can be considered as an interrelated problem, and perhaps some of the problems that we're facing are stemming from that we have been looking too narrow at some aspects. We can also say that if you're trying to solve a problem with AI, you're probably looking too narrowly on the problem. Rather, humans, context, and other technologies, they are involved, and we need to understand better. And we're not there. We don't have that complete understanding yet, but we need to focus more on understanding this, how they are involved and how they can play a role together. As engineers, we therefore need to consider more system solutions, but not only the technical solutions, but considering these solutions in some kind of social technical perspective, where societal aspects and ethics will be a part of everyday engineering work. And I think this is something that we try to educate our engineers for. We have attention to this in the education programs in our engineering schools at universities here in Sweden, and in the educational frameworks as well. And I think we see that in other countries as well, but it is very important. And then in following this also, when we talk about complex context, and of course solutions, they are combinations and adjustments of different methods, different logics that are playing together. And you can see this, this is difficult and this is challenging, but it's also exciting because it kind of brings our engineering discipline and the design focus, and I think the relevance of design, not the least, into a whole new light. So let us take on this challenge together.
So I'm afraid that we talked longer than we were asked to. We are of course happy to take questions if there are any, or comments would be nice as well.
I just want to quickly say, I think today's lecture is so appropriate, given that the two Nobel Prizes, yesterday and today, were given to the use of artificial intelligence. One in physics, with the discovery or invention of neural networks, both Hopfield networks and Boltzmann machine by Geoffrey Hinton, who did spend a couple of years at CMU. And today's chemistry Nobel Prize also has been brought in artificial intelligence. And I think it is very appropriate that even though those are science prizes, now what you heard today, or what is the role of AI in the engineering space, which has a lot more consequences than just in a scientific sense. With that, I'll turn over for questioning to the rest of you, and I'll mute my.
You mentioned, well, thank you very much for your very interesting talk. And you had a classification of social and engineering factors. I thought that in many situations, self-driving cars is an example, where intention will play an important role in making the decisions. And intention is very difficult to know. In an AI system, and I think intention is difficult to include either as a social factor or as an engineering factor. And of course, in our legal system, intention is determined ex post.
Yeah.
But in self-driving system, questions of intention in the examples you mentioned have to be resolved in real time, in a split second, when you don't have the information about intention or the evidence or the background. What are your thoughts on that question?
Many, perhaps. We don't have answers, but I think partly a question back to you. Intention, are you thinking about the intention of the system, or how the purpose?
Oh, intention of the participants in the system, the actors, human actors in the system.
Yeah.
You know, I mean, like the example you gave, this guy commit suicide. But at the time, somebody comes in front of the car, moving car, whether it's a suicide attempt or not is a matter of intention.
Yeah,
which
yeah,
the
absolutely.
AI system cannot know, and at least cannot know in that time until somebody goes and checks on records. So this person's background and psychologist records and so on, the treatment, etc.
Um,
So
yeah,
that's what I meant by intention.
yeah, I understand. Shall I first, and then you can continue? I think this is really interesting because basically we don't know. Without AI, we are not always sure about the intention of the people that are using the system either. With a car now, if we see somebody jumping in front of the car, then we also need to make some kind of judgment whether or not this is what this depends on, and this will be in a way the same with a self-driving car, and perhaps there will be several solutions that could kind of detect more of with some indicators what this could be and divide the reaction. But what is really interesting, I think, when artificial intelligence becomes part of the system, then in some way this also becomes some kind of more active actor or dynamic actor or agent in this system. And that creates a new kind of landscape. And one thing I'm thinking about, what we have been studying and posing a little bit when we talk about artificial intelligence brings generativity in the system can evolve beyond something that maybe the original designer has not intended, and perhaps we need to bound this generativity in some way, that generativity is allowed but to certain degrees and through other methods in the system to create bounded generativity in some way. This is a really interesting question, but those are the things that I'm spontaneously thinking about.
I think it's interesting that you're answering with judgment as part of intention, because judgment is also something that is really interesting to discuss. What is the judgment of the system? What is the judgment of the participants in the system? And what's the judgment of the interactions between these different actors? And that takes us to another key concept, I think, as well, that is trust. And maybe I can take a small anecdote of this. I was having lunch with the CTO of one of the leading companies for developing autonomous systems for cars. And he's a good friend since long. And we said, well, let's have lunch and let's discuss trust. Yes, we should discuss trust, we said. And I come to the lunch and I'm so happy to discuss how much can we trust the system and how should we take this perspective and what are the different types of trust that we should have. So there are many types of trust. So I really look forward to discuss this. And then I recognize from the opening words of my friend then that he's really looking forward to discuss how much can the system trust the input from the driver. So how much should he rely on that, and when is maybe the intention coming with something that is negative for the system, or they are confused with the situation the car is in. So his perspective was the other way around. How should we trust the human in this system? And of course, nothing of this is answering to your question on intent, but I think all those together, judgment, intent, trust, and others, underline the difficulty of having this discussion in society, and we really need to find the should we say more clean cut and simple discussion for driving it forward. And it's a true challenge.
Yeah, but I think it's still very important to understand that we have this issue of intention today as well, if it's not involving any intelligence solutions. But we have our ways to try to kind of understand this intention. For example, through judgment, through how we, in the social interaction, read each other's, how we judge situations, etc. So we need to find new ways to address this in the interaction between humans and intelligent systems.
Thank you.
Can I add to that? So one of the things that when we look at in an Indian context, people say that autonomous concept may not work in India, but I tend to have a slightly different view that maybe removing the intention of the driver itself is a major thing which can add value to India.
Yeah,
Right?
absolutely.
So
But maybe it will
because
be.
the picture that you have shown that the vehicles move around without crisscrossing or right, which may happen a lot more easier in an Indian context, but removing the intention itself uh, pushes the focus to the actual physical interactions and what we call a kind of affordances. So if the systems can rely on the physical properties and leave out the intentions in the modeling process, it may become a little more easier to deal with this rather than bringing intentions into the whole modeling context. That's one viewpoint I had on that. Second is when you are suggesting in terms of incorporating AI using the analogy of an aircraft, as you add more intelligence into a system, right? But AI has the potential for generativity. So which are you suggesting that it can also lead to reorganization of what we call as an aircraft?
Well, that's a nice question, isn't it? I think you already see that, if I stopped,
Yeah.
you see that there are changes to what an aircraft is. And if you go back 30 years in time, an aircraft was something that had a pilot on board. And that meant that it's a fairly large thing, it's a dangerous thing that is very expensive. But what we see today is that we have drones that are doing some of the tasks that aircraft used to do at a totally different cost level, and we have, well, quite an efficient approach, and you can typically see that rather than having one large aircraft solving a large problem, you have a number of small cheap drones solving the same problem, but also that you get things done that weren't done by the manned aircraft. And this has challenged the regulations for aircraft. So it's how do we do it when we are operating in traffic, when the pilot is not on board, wanting to save his own life, that is changing the conditions. But it's also changing the regulations on more odd ways. Before it was said that an aircraft is weighing 150 kilograms and more, and that was based on a pilot is 75 kilograms and as a standard, and then you need 75 kilograms to keep the pilot in the air. So nothing below 150 kilograms was an aircraft, but now it is. So it is changing, and I think we will see more changes both to what aircraft do and how they do it.
So
if we, yeah.
yeah, so which is where my point is that we should not probably look at controlling generativity in the sense to protect a system boundary, but also look at options where the system boundary can change
Exactly.
because of generativity. So
Yeah.
it becomes a more selective or a more nuanced understanding is required in terms of how generativity has to be used.
Yeah, how generative has to be used and what kind of still the bounds are of generativity to keep kind of this safety criticality under control. And here we have for organizations a really interesting challenge, because many of the organizations that have been designing and developing, for example, aircraft, have been working with kind of a lot of control methods to make sure that it will work. So, and if you then allow generativity, then all of a sudden this will be overturned. So this is a real challenge that we try to look into, and we don't have definitive answers yet, but most probably a combination of formal methods, solutions in the system, and also the role of the human will play a role in mitigating this.
But I think we should perhaps underline that it's a real issue. How do we combine generativity with safety criticality? It's in classical systems, and you saw in the architectural schemes that was a division between the flight control system and safety criticality and the mission computer, basically in two different levels. But when you can see that generative technologies play a more central role in achieving the safety, then you cannot ignore the generative technologies because they are contributing to the safety. So it's kind of a double-edged sword here, that you need to take care of those technologies in order to get the system that is state-of-the-art in its safety, in its ability to deal with unexpected situations, resilient perspectives. And so you cannot sit and wait, in a sense, but you need to bring in generativity to your safety critical system. And we usually call that the double-edged sword, and it's quite an interesting challenge.
Intriguing engineering, but not only engineering challenge. But we need to go back a little bit to the traffic in India, because this has been such a topic for between Gunnar and I for discussing as well. And I understand also from what we have been talking to Sub that there is some divide. Will autonomous driving ever be working in a traffic system that is similar to what we see in India, which is, in a way, it can be perceived for a person outside of the system as more chaotic. And I think that was also how you kind of defined it. When we were in India, we have had some lovely visits there, and we would really like to go back to India
to understand it better.
Yeah, and in my turn, I'm originally from the Netherlands, and I live in Sweden, and that's both Northern European countries, you can say, and with relatively rule-based standardized traffic, but still in Sweden the traffic is much less than in the Netherlands. There are a lot of car queues, and I could see kind of this kind of cultural difference. And when I go back now to the Netherlands, I really need to think, oh, I need to adjust myself to this new traffic. I thought in India there was some kind of system that you could detect, the system of mutual adjustments. And everybody seemed to know what to expect and how to drive and how to behave in order to make it work. And we have an example that where we got stuck in a complete traffic jam in Stockholm just because one car had crashed in a little bit wrong position, while when we were in India with a lot more traffic, even though it was not going so fast, traffic was still flowing in a sense, and maybe our observations are not that many, and I think maybe like you say that perhaps what the most challenge is that to make kind of more autonomous driving work together with manual driving in the same. But if it would be only the one or the other, then most probably the traffic system and the people involved in the traffic system, even pedestrians, they will adjust themselves to the new situation. But it will most probably entail a little bit more different challenges than have been kind of observed and taken care of in the US context or in European context, I would say.
But we would, of course, love to hear your views on the possibilities.
So the micro level negotiations definitely you see happening. We have scenarios where, for example, where there is no traffic signal, probably the movement is people don't have to wait for long compared to having a traffic signal where the queue builds up. But also one factor which need to be brought in is if you add the vehicle size or the vehicle physical structure and the size into this picture, that is where it becomes more complicated. If it were like, for example, two-wheelers, cycles and others which are more flexible, then you see a lot more easier way of managing the same situation. But the moment you have big cars and trucks and other things coming into play, then it becomes a more structured problem, which is difficult to deal with at a human level, because an individual sitting inside a vehicle may not be able to visualize that kind of flexibility in a larger vehicle compared to a smaller.
This will be very interesting to follow, actually, how this will play out. And I think we will see more discussion around that also across the different
Certainly.
cultural contexts. So,
Thank you.
In your talk, you use the word complexity and complex systems. I just want to clarify, is that word complex is used in the sense it is used in complex systems, or in the sense of complicatedness, something which is complicated? Because when you apply that complex to organizations, contexts, and systems, I just wanted to clarify what's the
very good
sense
question.
in which the word complexity is being used here. Thank you.
There is complexity theory that is something very specific, and that's not really what we are referring to. We are talking about complex systems as systems that are interconnected but still scalable in a sense, and
got it. Yes.
you cannot deal with them as a few individuals, but you need to have an organized, structured way to address them. And one of the theories, or what we should call it, that we rely on is complex product systems, and works by Hobday and Davis and others. So, but I agree, there are. It's really interesting to discuss what's behind the complexity, and you cannot only talk about complexity as such, but
no, and referring kind of to the complicated problems and the complex problems, and acknowledging that they are not the same. I think that's very important. But here in this case, we're relying more on a relation between there are many different technologies, knowledge bases, interrelationships, different elements that are interconnected and involved. And it's a combination where also humans play a role in kind of some system context. That's kind of basically how we conceptualize complexity in the way that we are using it.
Thank you.
Thank you.
welcome.
Thank you very much, Gunnar and Nicolette. It's been really a pleasure having you. Thank you very much for the lecture, and I'm so glad to be here with you while you're giving the talk. And I've had 2 wonderful days, and I hope you will come back and give more lectures, because we want this forum to be a place for us to exchange ideas, as well as to come up with also to educate each other with a wide variety of contexts, as we correctly pointed out. With that, I think I'll close the session unless there is somebody else who has an urgent question.
Sab, when is the next talk?
23rd October.
Yeah.
The next one will be on 23rd October. I think it is Chris Wood who will be giving a talk on 23rd.
Yeah, that is also on use of AI. Okay, thank you very much.
Let us just say thank you. We enjoyed it a lot. We look forward to learn more about India.
Absolutely. And please reach out if you have more questions or want to kind of discuss something with us.
Yeah.
Okay. Thank you.
Bye.
Thanks. Bye-bye.